Hello, my name is Anubhav Srivastav, and today I'll be presenting our paper, Elimination A/B Trees with Fast Durable Updates. This paper was written with the help of my co-author and supervisor, Trevor Brown from the University of Waterloo. Before I get started, I want to mention that all of the code and artifacts for this paper are publicly available, and the links to those are in the paper. The goal of this paper was to build a fast concurrent ordered dictionary, which supports the following standard operations. Insert, which attempts to insert key and val. It succeeds if the key is not in the dictionary and returns null. It fails if the key already exists in the dictionary, in which case it returns the existing value. Delete, which attempts to delete key and its associated value. Delete succeeds if the key is in the dictionary and fails if it's not. If it succeeds, it returns the deleted value, and if it fails, it returns null. And find, which searches for a key and returns the value, or null if it doesn't find it. Ordered dictionaries also often implement a range query function, which retrieves all values between a lower and an upper bound. The data structures that we present in our paper can perform range queries, but we didn't optimize for that case. In other words, our data structures are best suited for workloads with mostly finds, inserts, and deletes, with the occasional range query. Most ordered dictionaries are implemented using trees. Binary trees, being the simplest, were common at first. The problem with using binary trees, though, is that the lower down the tree in operation goes, the more likely it is that the operation will cache miss when following a pointer, which will hurt performance. It's previously been shown that most of the time spent during tree operations is spent during these cache misses, so reducing the depth of these trees is a good first step in achieving good performance. In balanced binary search trees, the path from the root of the tree to a leaf goes through big O of log base 2 of n child pointers, so that's log base 2 of n potential cache misses. To improve this, people started using B trees, which use fat nodes, each of which contain between b over 2 and b pointers. Often, b is chosen such that a node fits in a cache line, so essentially, once we follow the pointer to the node, we can read the entire node's keys and values without cache missing, because all the keys and values are in the same cache line. Also, since each node has at least b over 2 children, the depth of the tree is at most log base b over 2 of n, which can be better than the log base 2 of n from binary trees and lead to faster searches. Unfortunately, B trees, as they're used in single-threaded code, aren't very concurrency friendly. Consider an insert which increases the height of a B tree. In this example, suppose 4 is the maximum node size, so all of these nodes on the left are full. To insert the green key value pair, you would have to split the leaf and insert a new key and pointer in the leaf's parent. But the leaf's parent is full, so it has to be split too. This continues until we reach the root. When the root is split, the height of the tree increases. I've only shown 3 nodes here, but you can imagine a larger tree in which there might be many more. As you can see, height increasing requires exclusive access of all the nodes in the chain, which can slow down other operations. To avoid this problem, the trees we present in our paper are based on a single-threaded, relaxed A-B tree data structure proposed by Larson and Fagerberg. There are 2 ways in which the B tree constraints are relaxed. First, A-B trees can have between A and B pointers per node. A is chosen to be less than b over 2, so it's a less strict notion of when you have to merge nodes. For example, in our trees, A is 2 and B is 11. This allows for less frequent rebalancing at the cost of having worst case depth. The second way relaxed A-B trees differ from B trees is that large updates are split into smaller steps. In fact, updates affect at most 4 nodes at a time. This is much more concurrency friendly. Let's take a look at the example from before, but with relaxed A-B trees. Instead of locking all the nodes up to the root, we will split the leaf node and join the 2 halves by a temporary node called a tag node. The tag node is the orange node shown here. In the next step, we will replace this tag node with one closer to the root by merging it with its parent, splitting the resulting overfull node, and creating a new tag node closer to the root. If this is hard to follow, there's an example a bit later. In previous work, my co-author Trevor Brown created a lock-free implementation of the relaxed A-B tree. That implementation uses the multi-word lock-free primitives LLX and SCX, which are multi-word generalizations to the load-linked and store conditional instructions. The lock-free A-B tree performs well on read-mostly workloads, but it has slow updates because it replaces the entire leaf node on an update. In this diagram, we see when the key 3 is inserted, the entire leaf node has to be replaced. This is obviously expensive. The lock-free primitives also add some overhead. Finally, we have the context we need for the motivation of this paper. We wanted a tree which retains the performance of the lock-free A-B tree, but also performs well in update-heavy scenarios. In our paper, we present the Optimistic Concurrency Control A-B tree, or OCC A-B tree for short. Like the lock-free A-B tree, the OCC A-B tree is a concurrent implementation of Larson and Fagerberg's relaxed A-B tree. Some of the differences are the OCC A-B tree locks nodes before updating them to avoid conflicts between updates. Specifically, we used MCS locks, which are much more efficient than spin locks in multiprocessor systems. To deal with concurrent updates during a find operation, we use optimistic concurrency control, which is essentially a version number for each leaf. Inserts and deletes also modify leaf nodes in place instead of replacing entire nodes. Additionally, they leave gaps between keys, so deleting a key does not mean that other keys in the node have to be shifted. However, the keys of internal nodes of the OCC A-B tree never change, so if we want to add or remove a key from an internal node, we do replace the entire internal node. This makes searches simpler since they don't have to deal with the keys of internal nodes changing. Now let's walk through some of the operations of the OCC A-B tree. We start with the diagram on the top left. Deleting the key 6 is easy, it's simply removed from the leaf that contains it. However, this leaves the leaf on the right under full. To fix this, we merge the two leaves together. This requires changing the parent node as well, since it will have one less key after the merge. To perform this update, we first lock all involved nodes, then construct these two new nodes in local memory, then atomically perform the update by changing the appropriate pointer to point to the new subtree. Next, let's do some inserts. There are two types of inserts in the OCC A-B tree. The first is called a simple insert. An insert operation is a simple insert if there's space in the leaf that we want to insert into. This is the insert of 9e here. The second type of insert is called a splitting insert. Splitting inserts occur where the leaf we wish to insert into is already full. Similar to the fix under full case, we first lock all involved nodes, in this case the parent and the leaf node. We then construct the update by splitting the leaf, inserting the new key into one of the leaves, and joining the two halves together with a tag node, which is like the orange node we saw before. We then change the pointer in the parent atomically to point to the new subtree. Lastly, we have to remove the tag node. We want to merge the tag node into its parent. We do this again by locking all involved nodes, constructing the new nodes in local memory, and then changing a single pointer. A few more details about the OCC A-B tree. Each node has a lock, which is used by updates, and a marked bit. The marked bit is initially not set, but is set before we unlink a node from the tree. Updates check that no node involved in the update is marked before proceeding, which guarantees that updates only affect unmarked nodes, which are still in the tree. Leaf nodes also have a version number. The version number is incremented before an update's modification begins to an odd number, and again after the modification is complete to an even number. This means that if the version is even, the leaf is not being modified, but if the version of a leaf is odd, it might be being modified. Now let's talk about how find works. Finds start at the root and read internal node pointers until we reach a leaf. There, the find tries to read a snapshot of the leaf's contents while the version is even and not changing. That is, while the leaf is not being modified. If the find in the leaf detects that the snapshot is not valid, either because the version has changed or because the version is an odd number, the find rereads the leaf. Note that finds do not acquire locks at all. The snapshot is required because we don't assume that you can read a key and value together atomically. Without the snapshot, a find could find the correct key, but a delete could delete the value before find could return it. The OCC A-B tree is linearizable. That is, each operation appears to take place atomically at some point between its invocation and its response, and it returns the correct value according to the sequential ADT, in this case an ordered dictionary. The point at which an operation linearizes is called its linearization point. In the example below, the linearization points are shown by the red bars. The insert linearizes before the delete, even though it started after the delete. The insert returns null because it successfully inserted the key, and the successful delete returns the value that was inserted, in this case A. Let's take a look at some of the linearization points in the OCC A-B tree. Splitting inserts are easy. They linearize when the pointer in the parent node is changed to point to the new node. Note that the new key and value will appear in the tree as soon as the pointer is changed. For inserts and deletes that modify a leaf, let's consider an example insert and find operation and see how they interact. The linearization points you'll see in this example will be important to another contribution of our paper called publishing elimination that I'll get to later. Back to the example. The insert first locks the leaf and increments the version to an odd number. Suppose the find starts now. It will try to read a snapshot of the leaf's keys, but since the version is 1, which is odd, it cannot, so the find waits for the version to be even. The insert now inserts the key and value and increments the version to an even number. Since the version is even, the find is now able to read a snapshot of the leaf's keys by reading the version, reading the keys and values in the leaf, and reading the version again to validate that the version hasn't changed. The find can return immediately. Eventually, the insert will unlock the leaf and return as well. Since finds wait for the version to be even before getting a snapshot, we should linearize inserts and deletes while the version is odd. Specifically, let's choose to linearize at the last possible time, the second increment of the version. This choice will become important later when we discuss publishing elimination. Finds that reach a leaf that is in the tree linearize anywhere during their snapshot while the leaf's version is even and the leaf is not changing. To recap, inserts or deletes that modify a leaf linearize at the last possible moment when they increment the leaf's version for the second time to signal that their update is complete. Finds that reach a leaf that is in the tree during their snapshot linearize anywhere during their snapshot. I'm now going to very briefly mention the other linearization cases, but I encourage you to read our paper for a full description. For an insert that finds the key it's trying to insert has already been inserted, we linearize that insert at the read of the existing key. Similarly, a delete which finds that its key is already deleted can linearize once it is done reading all keys in the leaf. These reads are both done under a lock, so they're safe from concurrent updates. Finds that terminate at a leaf which has been unlinked from the tree can still read the leaf and return without restarting from the root. They linearize at the point when the leaf is unlocked, but again, for the sake of time, I'm going to leave the explanation to the paper. The OCC-AB tree is linearizable, but there are dozens of linearizable trees. We wanted a fast tree, so let's look at some performance results. The following experiments were performed on a system with 4 sockets and 36 threads per socket for a total of 144 hardware threads. The data structures have 1 million keys, and the keys are accessed uniformly. Looking at a read-mostly workload, we can see that the OCC-AB tree performs similarly to the existing lock-free AB tree by Brown that I mentioned earlier. This is pretty much expected because they're based on the same relaxed AB tree. But if we look at the update workload, we can see that the OCC-AB tree does much better. As I mentioned before, this is because the OCC-AB tree doesn't create new leaf nodes each time it does an update, and it also doesn't have the overhead of lock-free primitives. Elimination involves grouping and reordering operations in a way that reduces the number of total modifications to the data structure. Elimination was first discussed in the context of stacks by pairing up pushes and pops. Suppose we have 4 concurrent operations, 2 pushes and 2 pops. In a regular stack, we might have push 5, then push 7, then a pop, then a pop. In an elimination stack, however, we might have a push 5 which doesn't modify the stack yet, but waits for a concurrent pop, then a push 7 which also doesn't modify the stack and waits for a pop. Then, when a pop operation arrives, we pair up the concurrent push 5 and pop, so that the pop returns 5, and neither operation has to modify the stack. We do the same for the other push. Elimination is possible in dictionaries too. Recall that if a key is already present in the data structure, an insert does not modify the tree and simply returns the existing value. In this example, the green bars represent linearization points of the operations. Assume the key 5 is in the tree initially with value A. Suppose thread 1 successfully deletes 5 at time t and returns A. Thread 2 then inserts 5 again with value B and returns null. Then thread 3 deletes 5 and returns B, and finally thread 4 inserts 5 with value C and returns null. In this scenario, each operation is only inserting or deleting based on whether it finds the key in the leaf. But suppose that additionally, threads 2 to 4 know what key and value thread 1 deleted, as well as the fact that they are concurrent with thread 1's linearization point at time t. Then, thread 2 can instead linearize before time t and perform its insert before the key is deleted. Thread 2 now does not have to modify the tree and can simply return A, the value associated with 5 before thread 1 deleted it. Since thread 2 no longer inserts the key is not in the data structure at thread 3's linearization point either, so thread 3 also doesn't have to modify the tree. Finally, we can move thread 4's linearization point before the insert as well, to return the previous value, again A, and not modify the tree. By simply changing when to perform the insert operations, we've managed to remove 3 modifications to the tree. Similarly, if thread 1 was performing a successful insert, we could linearize all deletes of the same key before thread 1, making them have no effect, and keep all inserts after thread 1's insert. The main challenge of elimination is detecting concurrent inserts and deletes. We do this with a new technique we call publishing elimination. In publishing elimination, whenever an update modifies a node, it stores in the leaf an elimination record which contains the inserted or deleted key, the value that eliminated inserts should return, and the version while it was modifying the leaf. Other threads use this elimination record to find out whether they are concurrent with the successful insert or delete's linearization point, and if so, what value they should return. Note that the record doesn't contain a field for what eliminated deletes should return. This is because eliminated deletes don't modify the data structure by definition, and deletes that don't modify the data structure always return null. So we only need to store the value that eliminated inserts should return. In this example, we have an operation which either inserted or deleted key 5 with value A, and it did so while the version was 1. Recall that successful inserts and deletes linearize at the second increment of the version number, so in this case, when the version was incremented from 1 to 2. Let's think about how an insert or delete operation, call it O, could prove to itself that it was ongoing at the linearization point of the operation that published the elimination record here. I'll show an example on the next slide too. As soon as O reaches the leaf, it reads and stores the leaf's version. This is the earliest leaf version that O knows it was there for. O then reads a snapshot of the record while the leaf's version is even to ensure that the record isn't being modified. If the earliest version that O read was less than or equal to the version in the elimination record, 1 in this case, then O knows that it was there before the transition from 1 to 2. We also know that O was there after the transition because it snapshotted the elimination record while the version was even, and O was there while the version was 2 in this case. If the key of O matches the key in the elimination record, then O can eliminate itself. Let's see an example of elimination in action. The insert in this example will be eliminated. First, the delete locks the leaf and increments its version number. The insert then reaches the leaf and reads and stores its version as soon as it can. In this example, the insert knows that it was present when the leaf version was 1. The delete then deletes the key, publishes the elimination record with the deleted key and value and current version of 1, increments the version to 2, and linearizes at that point. The insert now resumes. It will try to eliminate itself by reading a snapshot of the elimination record while the leaf's version is even and unchanging. After reading the elimination record, the insert will try to figure out if it was present before the linearization point of the delete. Since the version it read previously, 1, is less than or equal to the version in the record, also 1, it knows that it was there before the linearization point. Also, by the time the insert reads a successful, consistent snapshot of the elimination record, note that the version is already even, 2 in this case. This means that the insert was present at the linearization point of the delete, and we can eliminate the insert by linearizing it just before the delete took place. The insert finds the value to return in the elimination record and returns A. Finally, the delete can finish up by unlocking the leaf and returning. Note that if the insert first reached the leaf after the version was already 2, it would not be able to guarantee that it was present at or before the version in the elimination record, which is 1, and so it would not be able to eliminate itself. Publishing elimination works quite well in practice. Our tests show that enabling publishing elimination doubles the performance of the OCC-AB tree on an update-only, skewed workload at high thread counts. On a 50% update workload, the difference is less substantial but still noticeable at high thread counts. Let's look at how the OCC-AB tree, with and without elimination, stacks up to well-known state-of-the-art ordered dictionary data structures. We group the compared data structures into two categories. The first contains those data structures that adapt to the increased contention or skewed key access, and so should theoretically be faster on skewed workloads. The second category contains distribution-agnostic data structures and includes some well-known concurrent binary search trees and B trees, as well as the lock-free AB tree mentioned earlier. The OCC AB tree, even without publishing elimination, is competitive with these state-of-the-art data structures on all workloads, and in many cases is significantly better. On a read-mostly workload with uniform key access, we can see that the low tree depth of the concurrent interpolation search tree and the AB trees leads to better performance than all of the other data structures. On update-heavy workloads with uniform key access, we see that the OCC-AB tree, with and without elimination, outperforms the competition, especially at higher thread counts. Finally, on an update-heavy workload with a skewed update distribution, the displaylist, Natarajan and Mittal's BST, and the OCC-AB tree without elimination all perform similarly at high thread counts, but, as we saw before, elimination helps the OCC-AB tree almost double its performance at the highest thread count. We also ran the Yahoo Cloud Serving Benchmark, or YCSB, which is a database benchmark using a provided dictionary as the database index. Because the benchmark is only using the data structure as an index, it's essentially an insert-only workload, so there's no possibility for elimination. Still, the OCC-AB trees performed quite well compared to the other data structures. The leading data structure here, the concurrent interpolation search tree, does particularly well because there are no delete operations, but our experiments on the previous slides show that it scales poorly with deletions. The final section of our paper describes the changes required to make the OCC-AB tree persistent. Persistent memory consists of volatile memory backed by persistent main memory. The volatile memory is lost upon power failure, but as the name suggests, the persistent main memory is persisted. The changes to make the OCC-AB tree persistent are simple. We flush and store fence after writing keys, values, and pointers, and we use the link and persist technique, introduced independently by David et al. And Wang et al. To ensure that searches don't end up at nodes that are only in volatile memory and aren't flushed. The OCC-AB tree doesn't use any write-ahead logging to guarantee persistence, which keeps updates fast and the recovery procedure simple. For the sake of time, I'll leave a full description to the paper. Performance-wise, we found an average overhead of 10% upon turning on persistence, which is comparable to other persistent trees, but this value might change based on your workload. We also compared the persistent OCC-AB trees to other trees and found that it scaled much better with increasing threads. These experiments are run on a system with around a terabyte of Intel 3D XPoint NVRAM. The system is a 4-socket system with 24 threads per socket for a total of 96 hardware threads. That's all I have for this talk. If you're interested in learning more, please check out our paper and feel free to reach out to me if you have any questions. There's also an extended version of our paper out on arXiv with proofs and some more performance results if you're interested. Thanks for listening.